Okay, very good morning. I welcome you all for the machine design second design of spur gears. So, beam strength. The beam strength formula, beam strength is given by MB sigma By, where M stands for the module, B stands for the face width. It is generally assumed as 10 times of module. Sigma B is the permissible bending stresses for the material, and Y is the Lewis form factor. So, Earl Buckingham. So, according to Buckingham, the sigma B, Buckingham suggested that the endurance limit stress of gear tooth approximately one third of ultimate tensile strength. So, based on this, the endurance limit, the sigma B is generally taken as one third of SUT. So, it is in many times it is given that SUT is equal to 600 Newton per mm square. So in calculation, you will write down sigma B is equal to SUT divided by 3 or 1 by 3 into SUT, and then 200 divided by 3, sorry, 600 divided by 3, you will write sigma B is equal to 200 and you will proceed further. So according to Earl Buckingham's, this sigma B is one third of SUT. This value we will be considering while solving the problems when ultimate tensile strength of any material is given and we have to proceed further for the calculation. Now, today we will be discussing about effective load on gear tooth. Many formulas are there for effective load calculation. So, there are two basic different methods to calculate the effective load. We have already discussed, or it is always desired that your effective load and beam strength and wear strength. Beam strength we have discussed. It is the maximum tangential load that the tooth can carry without bending failure. And SW is the wear strength. We can say that the maximum tangential load the teeth can carry without pitting failure. So your beam strength and wear strength, both the strengths should always be greater than P effective load acting on the gear tooth. By how much amount? By an amount of, we will call it as, for example, 1.5 times. So that is 1.5, it is nothing but the factor of safety. So by this amount, they should be maximum. So in this way, we have to proceed for the numericals. Now, what is the effective load? We have discussed about ESB. We will be discussing about ESW. But what is the effective load? So let us see in this, we will be discussing effective load, the components, the two methods of effective load, approximate estimation method and precise calculation method. What are the different things and formulas in approximate estimation and what are the things in precise calculation? That all things we will be discussing. So to determine the tangential component of the resultant force between two matching teeth, two equations are used. So yesterday only we already discussed about the CMT. So torque transmitted by the gear is given by 16 to 10 raised to 6 kilowatt divided by 2 pi n. If kilowatt, the power is given to you and n RPM is given to you, then by putting these two values, you can easily calculate MT, the torque, and the torque again Newton millimeter. So, and based on this torque, the PT is nothing but the tangential force is equal to twice EMT by D. We have discussed yesterday the formula like this. MT is equal to, we have discussed the formula MT is equal to, you can say PT into D by 2. So this is the formula we have discussed, PT into D by 2. So based on this, the formula is written here that PT is equal to twice EMT divided by D. If we are considering here pinion, then it will be diameter for pinion. Okay, so it is the diameter for pinion. Okay, so we can calculate PT by using this formula. The value of tangential component therefore depends upon the rated power and rated speed. See here, the value of PT, it will completely depend upon MT. MT is the rated power. And the rated power is again depending upon the rated torque, and rated torque is depending upon the rated power. Okay. So what is this rated word is used here? So there are two concepts. We are designing at rated one, and there is one concept is maximum power and maximum torque. So we are not considering in our equation as maximum. We are considering as rated. Whatever RPM is given and whatever power is given, Based on these two, we are calculating torque and we are calling it as a rated torque and rated power. In practical application, now I will explain you that what is the concept of maximum and what is the concept of rated and what is the relation between this rated and maximum. This we will be discussing now. In practical application, the torque developed by the source of power varies during the work cycle. See, the torque varies continuously. Similarly, the torque required by the driven machine also varies. These two sides are balanced by means of a flywheel. So we have learned the concept of flywheel. So in this case, the torque required by source, for example, electric motor is there. It is producing the torque. So there are chances that the fluctuations are there and the torque may vary. I am just giving you one example of electric motor. And other side, on which your electric motor, one gearbox is there, and the gearbox is connected to any one of the mill, kiln, or any application or any crushing operation. So at that place also, depending upon the load, sometimes torque required is higher, sometimes torque required is lower. So the driving torque is also varying, driven torque is also varying, and these are adjusted by means of a flywheel. So in gear design, the maximum force due to maximum torque is the criteria. See, we have to take in account always the maximum torque and the maximum force. Means if I will say maximum torque, it will be MT max. And if I will calculate PT on based on it, then it will be PT max. This should be the criteria. This is accounted by means of a service factor. Now here the concept of service factor is used. So what is the concept of service factor? Here it is mentioned that CS. Okay. So here CS, service factor, is given by maximum torque divided by rated torque. What we are calculating, it is rated, and CS is the maximum torque. So CS I can write MT max, maximum torque, divided by MT. This MT which we are calculating in our generalized formulas. PT, and again if I substitute, see I have already given you MT is equal to PT into D by 2. So if I will substitute here PT into D by 2 for maximum, again MT is equal to PT into D by 2. Then D by 2 cancel, and you will get, it will be PT max divided by PT. So service factor is given by maximum torque divided by rated torque. And if you convert it, then it will be PT max by PT, the maximum load divided by, or maximum tangential load divided by the rated load PT. Okay. Now, where PT is the tangential force due to rated torque. So what we are taking in account, MT, PT, these are based on the rated. And what is maximum? It is the maximum occurring during the cycle. Maximum torque during the cycle. So rearranging the terms, I can say MT max is equal to MT into CS, or I can say PT max is equal to CS into PT. So PT max is equal to, taking PT on another side, then I can say CS into PT. Okay. Now I will explain you the concept of this, what is maximum. So for electric motors, electric motors, take any electric motor. The service factor is given by not maximum torque. It is clear cut mentioned as starting torque. Starting torque divided by rated torque. So it is assumed that for electric motors, the maximum torque is at starting torque. For starting the motor, whatever the torque is required, it is generated at the starting, it is always maximum. Therefore, it is not written here maximum, it is written here starting torque. Okay, one simple example I want to give you before proceeding further. If you are driving a bike, and if you want to, means you are moving on a certain, you can say certain inclination. Oh, some height is there, or some, you can say uneven portion is there, and which you want to go it at some height, or you may be driving in some hilly areas. Okay, you are getting my point. No plain road is there, some inclination is there, and you have to go for that inclination, etc. In Marathi you can say, I will take the help that घाटामध्ये जेव्हा एखादी गाडी असती तेव्हा जे चढ उतार आहेत कंटिन्यू त्या ठिकाणी, or you can take the example when you are coming to our college. Very simple example I will give you that you can understand. So when you are coming to our college, when you pass the boys hostel and then coming up to our main gate, the road is not straight, there is somewhat inclination. So is such inclination of road is there, or you have to go over some high upper area. So the next road, whatever the road you want to go and whatever the road is at bottom. So there is some inclination. Then what you are doing? You are driving your bike on first or second gear. You are not using your bike gear as third or fourth. Just imagine why. Because at that time, RPM is not the criteria. Your bike require more torque, more power to complete that inclination, to drive along that inclination. And if you are on a smooth road, plain road, then in that case, what your criteria? You can go for fourth gear, or if there is a fifth gear, also you can go for, because at that time torque is not the criteria. See, you can normal average torque, rated torque, you can proceed further. So see the difference. So if I will design the bike based on the normal circumstances, definitely it will fail. I have to take in account, for example, I am telling, I have to take in account the inclination. I have to take in account the inclination when it is, you can say, moving on a road or to some upper side, some inclination, then you have to go for first gear. So like this. And again, you may experience this type when our four-wheeler also, state transport buses also, when they will also move, you will experience that when depending upon the road condition, the bus driver is going on only first and second gear, continuous motion for maybe half an hour, etc. You can experience. So like this, this is just what example I want to give you, that this is the maximum torque. So for your bike, for assuming that you are coming to college, then whatever the maximum torque required from your home to your college gate or your our main porch area, so maximum torque you will require at the inclination from boys hostel to our college gate. So this is the maximum torque, and service factor is equal to this maximum torque divided by rated. Rated is the general torque which we are considering for our calculation purpose. So it is rated torque. So just I want to give this example for more understanding purpose. So service CS, service factor, is given by maximum divided by rated, and CS is nothing but starting torque divided by rated torque for electric motor. For other cases, I will say maximum torque divided by rated torque. How to take in account? While solving numericals or in any design, there are two cases given. Directly it is given that service factor is equal to 1.25. No problem at all in such case. But if it is given that the starting torque is 150% the rated torque, the starting torque is 150% the rated torque, it clearly indicates that your CS is equal to 1.5. The maximum torque transmitted by the machine is 125% times the rated torque or normal torque. Then you can say that CS is equal to 1.25. So in this way, you have to take in account while solving the numericals, while considering this part service factor in your design of spur gears calculation. Okay. Now this service factor, how it varies? There are some considerations. Let us go just more deeper. So I hope that while I am discussing this all and giving examples by giving the heading effective load, you might have taken down at least the formulas for CS. So the value of service factor given in table 1. There are again table 2, table 3. Just have a look for table 1. Service factor for speed reduction gearboxes. This is a generalized case for your understanding purpose only. So working characteristics of driving machine. Again, I will be discussing what is the driving machine characteristics, what is the driven machine characteristics. So first to concentrate on working characteristics of driving machine, working characteristics here I will say of driven machine. So driven machine and driving machine working characteristics. For uniform driving to uniform driven, no problem at all. Service factor 1. Uniform working conditions for driving machine, moderate shocks are there for driven. It is taken as 1.25. Uniform driving conditions, driving machine conditions, and heavy shocks at driven, it is considered at 1.75. See, driving machine is uniform, but the driven conditions are changed. Then the service factor is varied from 1.25 and 1.75. This is the first case. Okay, now second case, driving also some shocks are there, light shock. Driven, but driven is uniform, 1.25. Driving light shock, driven moderate shocks. 1.50. Driving light shock and driven heavy shocks, more shocks are there. It is 2. So service factor is taken as 2. Now driving machine, it is operating at medium shocks and driven machine is uniform 1.5. Driving machine is medium and driven also moderate 1.75. And driving is having some medium shocks and driven is at heavy, then you can see the CS is 2.25. So very important consideration here. Uniform, very first case. And last case 2.25. So just to see, this depends upon the condition. Now let us understand what is this driving and driven cases. Just have a look. Examples of driving machines with different working conditions. Characteristics of operation. Driving machine. Uniform. When I am saying it is uniform, so you can say it is electric motor, steam turbine, gas turbine. So electric motor, one constant RPM is there and it is rotating at some constant RPM. And again, so no any shocks and vibrations are there. So it is uniform. When I am saying light shock, at driving, it is multi-cylinder internal combustion engine. Many cylinders are there. And when I am saying, means here it is mentioned that medium shock at driving. So in this case, single cylinder internal combustion engine is there. Single cylinder internal combustion engine. So this is the condition. So for driving machines, when we will call it as uniform electric motor, 1 CT tire rotating at 1440 RPM, no any external disturbances. Light shocks, when the power source is like multi-cylinder IC engine, so there are some shocks, and only single cylinder is there, then there whatever the strokes are there, depending upon the strokes, it will vary. Okay, the examples of driven machine with different working conditions. Now we have discussed about driving. Now let us concentrate on driven machines with different working conditions. So driven machine, when I will say uniform, then generator, belt conveyor, platform conveyor, light elevators, electric hoist. So driven machines also uniform, no problem. Mixer with constant density material. This is one when anyone is mixing with constant density material. So it will be uniform. Then medium shock at driven side. So main drive to machine tool, any machine tools, heavy elevators are there for up and down motions. Then turning gear of a crane, mine ventilators, mixer of variable density material. So material is having some variable density. Then the same mixer with constant density, uniform, with variable density, it will go for medium shocks. And heavy shocks, we all have discussed or know this application of heavy shocks. So very first press machines. So press machines, forging, like this press machines, or you can say any other operation where the press tools operation is used. So it is press machine. Then mills are there, rolling mills where the material is complete rolled, forming rolls from a plate, heavy centrifuge, heavy feeding pump, then rotary drilling apparatus. So like this, different mills are there. So heavy duty applications are there, and where manufacturing sector, forging sector, like these machines are there. So at that particular place, the driven machines having some these characteristics as uniform, medium, and heavy. And we have discussed based on the driven and driving characteristics how the service factor is varying. And in the numerical, it may be given that this is the service factor. Now, after the service factor, let us move to what is the need for dynamic load consideration. See, we have discussed about the static load PT. We are having some formula for calculating the static load PT acting on the gear. Now, why P effective is required, or what is the necessity so that one should go for consideration the dynamic load for a gear design? So when gear rotate at very low speed, almost zero velocity, or you can say minimum velocity, 5 RPM, 10 RPM like this, then PT can be considered at the actual load between the two machine teeth, no problem. When it is rotating at very lower velocity, I will not say zero, because if you say zero, then no rotation is there. So either static conditions or lesser RPM. So in this case, the dynamic load can be neglected and we can say that PT is the only load which is acting between the meshing teeth. But however, the gears are made for power transmission. Again at higher RPM, therefore gear rotate at appreciable speed. Let us assume that 1000 RPM, 1500 RPM like this. And it becomes necessary to consider the dynamic force. Due to this, dynamic forces also acting on the gear, and we have to consider the dynamic forces in the design of gears in order to calculate the module and further dimensions of the gear so that it will not fail during working conditions because of this effective load calculation. So we have to consider the dynamic load also. The need for dynamic load consideration. The dynamic force is induced due to following factors. So very first you can say inaccuracies of the tooth profile. Whatever the tooth profile is designed, if it is not machined as per requirement, definitely inaccuracies will be there. And this second, errors in the tooth spacing. So errors in the tooth spacing, it is manufacturing defect of tooth thickness. If tooth thickness is somewhat plus minus or not in tolerance, then it will affect the tooth thickness and inaccuracies of tooth profile. So these two are there. You can say the manufacturing not proper or manufacturing defect of the gear, not machined as per requirement, and due to this dynamic load can occur. Then misalignment between the bearings. If the bearings are not aligned as per requirement, bearing is an element which permits the relative motion between two parts. We will be discussing these bearings separately and all other aspects, bearing types, etc., design considerations, selection of bearing from catalog. It is some different bit. So if there is misalignment, the bearings are mounted on the casing or housing of the shaft. So if the bearings are not mounted as per requirement, or if there is some misalignment, the gear will also carry the same misalignment because the shaft is mounted in the bearing and it will rotate. And due to this misalignment, it will lead to some vibration, shocks, noise, and ultimately lead to dynamic load on the gear. Then elasticity of parts and inertia of rotating disc. Elasticity of parts, this is the concept elasticity and plasticity. If the gear is having some elastic properties, elasticity to regain its original shape and size after removal of forces. So it is subjected to some of the loads. So if due to the loads it is getting deformed, it is not allowed. So due to this deformation, the shape will not, the tooth profile will not as per requirement, and this will cause the unnecessary dynamic load. Inertia of the rotating disc. So whatever inertia caused due to the rotating parts, it will also have some effect, adverse effect. And these are the, I can say, few causes. These are the few causes for the dynamic load acting in the gear, and due to this, one has to consider the dynamic load. Okay, up to this, we have discussed about what is the need for considering the dynamic load into account. Now, let us see how to calculate the dynamic load. So there are two methods. First method is approximate estimation by velocity factor in the preliminary stages of gear design. And second method is precise calculation by Buckingham's equation or Scott's equation in the final stages of gear design. So whatever up till now we have discussed, this is the theoretical part giving the significance, but now we will be discussing about the approximate estimation and the precise calculation. These are the some of the important formulas. I will give you some time and you write down these formulas also. So there are two methods to account this dynamic load. We will be calculating P effective based on these two methods. So first method is approximate estimation by velocity factor. The name only indicates approximate and precise. First method, approximations are there. When no any dimension in our hand, module we don't know, then face width and PCD and all other things are not calculated. And in this case, we have to go for calculation of this effective load. Then some assumption method is there. Approximate estimation is there. We have to calculate P effective by this method. And second case, when we are having the module, then based on the module piece circle diameter, then face width and all the errors also we can calculate. All things we can calculate. It is the precise estimation of the dynamic load or effective load acting on the gear good. So let us concentrate on first method, method number 1. The formulas are very, very important while solving the numericals. Method number 1, approximate estimation by velocity factor for calculating the effective load acting on the gear. So as I mentioned, it is very difficult to calculate the exact magnitude of dynamic load in the preliminary stages of gear design. We don't know, we are not having the values of module, and due to the module face width and piece circle diameter and all other details, addendum circle, dedendum circle, whatever things are required. So in this case, velocity factor method of velocity factor CV. CV is the velocity factor developed by Barth. This the method is developed by Barth. It is also called as Barth velocity factor or velocity factor method. So we have to calculate the velocity factor CV, and there is one formula in which we will be using this velocity factor and we will get the value of P effective. So here there are 3 different formulas for calculation of velocity factor. So first, for ordinary and commercially cut gears made from cutters and with this velocity less than V is the pitch line velocity. Well, pitch line velocity less than 10 meters per second. Approximations are here. The CV 3 divided by 3 plus V. This is the formula. CV is the velocity factor and V is the pitch line velocity. For first case, ordinary and commercially cut. In general purpose gears are there, not much more accuracy is there, and it is operated for V less than 10. So general purpose application. For accurately hobbed and generated gears, see the gears are made by hobbing and generating process. Generating process, there are some process like profile generation. Some machines are there, MAG generation method. So rack, by using rack cutter, directly the complete teeth is made. And hobbing process we have already learned in subjects like manufacturing technology or MP. So by using this is somewhat accurate as compared to first gears and with velocity less than 20. So here we can say greater than 10 but less than 20. So CV is equal to 6 upon 6 plus V. This we have to use the formula. And third, for precise gears with shaving, grinding and lopping operations. These are the gear super finishing operations and having velocity, pitch line velocity greater than 20 meters per second. In this case, CV is equal to 5.6 divided by 5.6 plus under root V, where V is the pitch line velocity. Friends, why I am calculating? Let us have a look. P effective is equal to CSPT by CV. CS service factor, PT tangential load and CV velocity factor. So for this we are calculating the CV, first approximate estimation. So once again I will repeat, V is the pitch line velocity in meters per second, and based on the 3 conditions, when the condition is mentioned that the gears are commercially cut, you will directly take CV is equal to 3 upon 3 plus V. When it is mentioned the gears are hobbed or generated, the gears are generated, this word is there, you will take CV is equal to 6 upon 6 plus V. Or when it is mentioned that the gears are also carried for super finishing operations like shaving, grinding, lapping, any one of these name or just super finishing operations, then we will take the formula CV is equal to 5.6 divided by 5.6 plus under root V. So I will give you 2-3 minutes for writing this. Please write down. The velocity factor CV for first method, approximate estimation by velocity factor, the 3 different conditions and how to calculate the CV for the three different conditions. This just you have to write down. Or please give confirmation. Anyone? By putting in chat box. Abhinay. Okay, so let us move further. This is the CV we have calculated. Now, I have mentioned you that V is the velocity factor. Sorry, pitch line velocity. CV is the velocity factor and V is the pitch line velocity. In every of the last three formulas, there is 3 upon 3 plus V, 6 upon 6 plus V, and 5.6 divided by 5.6 plus under root V. So what is the V? V is the pitch line velocity, and it is calculated by, or it is calculated as V is equal to pi dn divided by 60 into 10 raised to 3. Pi dn divided by 60 into 10 raised to 3, where d is the pitch circle diameter in millimeter and n is the RPM. Pi dn divided by 60 into 10 raised to 3. This is the formula for V. You know V, then you can calculate CV. And if you can calculate CV, then see this is next formula for P effective. P effective is given by P effective is equal to CS into PT divided by CV, where the P effective is the effective load acting on the gear by considering the first method, that is precise estimation of dynamic load. By using this, we are having the formula where CS stands for the service factor we have already discussed. Then PT is the tangential load acting on the gear tooth, and CV is the velocity factor. We will calculate the CV by any one of the formula based on how the gears are machined. The velocity factor is an imperial relationship developed by the past experience, CV. The method for calculating dynamic load has the following advantages. By using this method, approximate estimation, it is much easier, very easy to calculate the velocity factor and design the gear. Velocity factor have sanctions of AGMA, American Gear Manufacturers Association, and they were used in the past for many years and giving satisfactory results. So though this method is precise, approximate estimation, still it has been used from long past and it has proven or it has given good results, so that one can rely on the design based on this approximate estimation method, first method. This is also having the disadvantages. The dynamic load will depend upon the mass of gears, then the mass connected by gear shaft, the other properties of gear material like modulus of elasticity. So these all things we are not considering. It assumes that dynamic load depends only upon pitch line velocity. So whatever these parts are there, so different masses of gear, then mass having the mass effect, the modulus of elasticity, its effect. It's due to modulus of elasticity, the deflection of one of the material is more as compared to other. And it is having also effect on absorption of shock and energy, and it will result in reduction in dynamic load. So whatever all these factors are there, all these factors are not considered. Only it is assumed that it is based on pitch line velocity. So this is one of the drawback of considering approximate estimation in the preliminary stages of gear design. Second, use of velocity factor is restricted to a limited range of pitch velocity. It is not possible to extrapolate the values. So for limited ranges, this method is used. So once again, I will repeat, when you are not having any data in your hand, approximate estimation is used. Further, you can go for precise calculation also. So This we have discussed. P effective is equal to CSPT by CV. This is the approximate estimation of P effective for considering the dynamic load into account. This is the first formula. P effective is equal to CSPT by CV, where P effective stands for the effective load in Newton. CS stands for the service factor. PT is the tangential load in Newton, and CV is the velocity factor. For calculating this CV, three different formulas are there. Then next, second method, I will say here, the method number 2 as effective load by using Spot's equation. Method number 2 as effective load by using Spot's equation. This is also mentioned as precise estimation, precise calculation method. So it is started only in the final stages of gear design, when the gear dimensions are known, when the errors are specified, the quality of gear is determined, the dynamic load equations can be calculated by Earl Buckingham, or we will be focusing here more on this Spot's equation. So we can calculate this by using the Spot's equation. So in this case, the effective load is given by P effective is equal to CSPT plus PD. In the last equation, we have seen P effective is equal to CSPT divided by CV, approximate estimation. Now precise calculation, it is mentioned as P effective is equal to CSPT plus PD. CS is the service factor, PT is the tangential load, and now the one term is new in this PD. So PD can be calculated by using Buckingham's equation. PD can be calculated by using Spot's equation. So there are different methods. We will discuss here how to calculate the PD by using Spot's equation. When we can use the method, once again I will repeat, the method is useful only when the gear dimensions are known. Means what? Module, by considering module, face width, pitch circle diameter, tooth thickness, tooth errors, everything you can calculate. Errors are specified. What is the type of error for this particular gear? And gear quality is also determined. So if everything is known, then and then only you can proceed for this formula, precise estimation or precise calculation of the gear tooth. So let us see how Spot's equation is there. No problem. So let us see how this Spot's equation. So P effective is equal to CSPT plus PD. So PD dynamic load based on the Spot's equation. The dynamic load can be calculated as there are three different formulas for steel pinion and steel gear. The dynamic load PD can be calculated as, see the formula, PD is equal to ENPZP into B into R1 into R2 divided by 2530 R1 square plus R2 square. So you will take down that this first upon the precise calculation formula. P effective is equal to CSPT plus PD. P effective, it is the effective load. CS service factor, PT tangential load, and PT is the dynamic load by using Spot's equation. Now we are discussing here the Spot's equation formula. There are three categories in the Spot's equation. Category number 1, when the steel pinion and gear are both are made up of steel material. Both are made up of steel material. This is category 1. Then second category, when both are made up of cast iron material. When both are made up of cast iron material. And third category is when pinion is made up of steel material and gear is made up of cast iron material. So for these three categories, the formulas are different. So by discussion, in the discussion time also, please take down this formula. So PD is equal to ENPZP. E stands for error. Again, there are some calculation formulas for this E, error. The error is the total error. The error is given by EP plus EG. So E is given by error for pinion plus error for gear. In the next slide, I will show you. NP, RPM for pinion, speed for pinion, no problem. ZP, number of teeth on pinion. B, face width is equal to 10 times of module. R1 and R2 are the pitch circle radii of pinion and gear respectively. R1 and R2 pitch circle radii of pinion and gear respectively. divided by 2530 under root of R1 square plus R2 square. I already mentioned what is R1 and R2. So by using this formula, you can calculate the PD and put your PD value in this equation. I will say this above equation, and you will get the value of P effective. If I will take value of put value of PD here. So this is the formula for steel pinion with steel gear. Now cast iron pinion with cast iron gear. See here. Error, total error, EP plus EG, RPM, NP, number of teeth on pinion, then this is face width, and R1 and R2 are the pitch circle radius of pinion and gear material respectively. What is the change? In the above formula it is 2530. In this formula it is 3785. So this is only change for cast iron pinion and cast iron gear. All other things are same. And last case we will discuss for steel pinion and cast iron gear. So pinion should be always be stronger. So here cast iron pinion and steel gear is not mentioned. So it is mentioned that steel pinion and cast iron gear. So E error, then NP, number of teeth on pinion, ZP, N RPM, ZP, number of teeth, B face width, R1, R2, pitch circle radius. What is the change in this formula? Here it is mentioned. The constant is 3260. This is one change. And under root of R1 square plus R2 square. So it is under root of R1 square plus 0.92 R2 square. So these are the three formulas based on the pinion and gear material. You will be using any one of the formula and you will calculate the PD. And after calculation of PD, I will put in the formula of P effective and I can easily calculate the formula of P effective. So much more time is given for this writing. So the actual dynamic load is less in the following cases. So it is generally that the dynamic load is always lesser than greater than static load. So your answer is dynamic load is always lesser than or static load is always more than dynamic. So any type of the question may be asked, your answer should be fixed. So dynamic load is always less than static load. Oh, so small gear transmitting low power. When the general condition dynamic load is less, when the gears are small, power transmission is low. High speed, light load gears are there. Small gears are mounted on smaller shaft, up to 50 mm diameter shaft, and small gear transmitting less than 15 kilowatt power. So these are some of the circumstances when the PD is observed to be lesser, when the PD is observed to be lesser. Okay, now in all the three formulas we have discussed about E, error. So what is the error? So the error is given by total error. Error is given by E is equal to EP plus EG, where EP stands for error for pinion and EG stands for error for gear. So write down this E is equal to total error is equal to EP plus EG. EP error for pinion, EG error for gear. When we will be solving one numerical, at that time you will get the complete idea how this EP and EG are calculated. Now error is based on the 12 grades are there for this error. There are 12, grade 1 to grade 12 are there for this error. So error, it is based on this formula. So here error for grade 1 is given by 0.8 plus 0.065. Error for grade 12 is given by 63 plus 5 times phi. Psi. And what is this psi? The psi is phi is given by, this is the formula for phi. So phi is the tolerance factor for the particular gear. The formula for tolerance factor is constant. Tolerance factor phi is equal to m plus 0.25 under root of d, where d stands for the pitch circle diameter for pinion. If we are calculating it for pinion, I will use dp. If you are calculating it for gear, I will use dg. So I can calculate phi for pinion. I will calculate phi for gear. M stands for the module. And if I will calculate phi, then I will put error. So if I will take grade 12, I will give you one example. If I will take grade 12, then error is equal to, the formula is 63.00. This formula I am using. Plus 5.00 into 5. So you have calculated 5. So I will calculate this formula for EP because phi is different for pinion and gear. I will calculate EG. Very important. You will get the answer in micron. Very, very important. After calculation, you are getting the answer in micron. And if you will put this answer in our this formula PD, definitely your final answer will be wrong. So here all things should be in mm. So you have to multiply by 10 raised to minus 3 and then only you will get the answer. So E is equal to EP plus EG. I will calculate EP. I will calculate EG. How EP is calculated? EP is equal to 63 plus 5.05. So in this 5 I will write down M plus 0.25 dp. So I will calculate error for pinion. I will calculate error for gear and then I will proceed. So when we will solve a detailed problem based on this error calculation and we will go for calculation of dynamic load, then you will come to know exactly that how it is required to be calculated. Now there are different 12 grades. So the method of manufacturing gear depend upon different grades. Gear 11 and 12 are manufactured by casting. Then grade 8, 9 require rough and fire hobbing. So depending upon the manufacturing process. Gears of grade 6 are obtained by hobbing, rough grinding. And gear 4, grade 4, shaving and finishing operation. So in the numerical itself, it is mentioned that the gears are machined to grade 8, the gears are machined to grade 12. Whenever there is grade is given and grade formula is given, you have to use for second method only precise calculation by using Squat's equation P effective is equal to CS PT plus PD. When the gear grade is given, any one of the formula is given for EPEG or any grade is given, then it is implied that you have to go for second method only. So these are the sum of the tolerance and grades. So we have discussed today